Please.
Good afternoon all. I'm a second year PhD student at Open University, United Kingdom. So my PhD project is on how to quantify the inelastic strains in creep fatigue deformation using misorientation mapping. But since that's not related to the scope of this conference, so I am presenting some work that I did on my initial stage of my PhD on a reheat crack using EBSD. So the topic of my today's presentation is plastic deformation around a reheat crack in an austenitic stainless steel weldment investigated by misorientation mapping. This project was done under the supervision of Dr. Shirley Northover, Dr. Hidia Jesseri, who is sitting here, and Professor John Bouchard. So, reheat cracks. So, intergranular reheat cracks occurs on non-stress relieved heat affected zones of 316H austenitic stainless steel weldments. When after welding, they are again prone to heat treatment or service temperatures above 500 to 700 degrees Celsius. At these temperatures, because of the carbide precipitations, the grain interiors are strong, so which prevents the deformation within a grain. So as a result of that, when the residual stress relaxes, the elastic strain is converted to plastic strain, and since the grain interior is strong, it cannot accommodate that large change in plastic strain. So this plastic strain is accommodated by formation of cavities along the grain boundaries, and later these cavities link to form micro and macro cracks. So in order to improve the life assessment methods at high temperature components, we need to understand the mechanisms of reheat crack initiation and growth in a microstructural level. So my study, it gives some insight into the extent and pattern of reheat crack, the plastic deformation around a reheat crack and the grains around it, using electron backscatter diffraction. So this is the component which was removed from a power plant because of the formation of a reheat crack at weld S4. So you can see the crack, and this is the weld. And this shows the optical image of the reheat crack around the weld. And it's very clear from the optical images that the crack is basically not continuous in nature, and it's also intergranular. So my study involves two parts. One at location 1, 2, 3. Around the crack I have done EBSD measurements and have compared that with a micro hardness. And after that, my second part involves EBSD scans along the line B2 and comparing the results with that of a study conducted by my supervisor Hedia on small angle neutron scattering, and to tell how EBSD can be used to predict or identify the cavitation sites in the material. So electron backscatter diffraction. Though on a macro scale the damage seems to be homogeneous in nature, but in a micro scale it's inhomogeneous because of the polycrystalline nature of the material. So EBSD is a very good approach along with the scanning electron microscope, where you can quantify the damage with respect to the local change in misorientations in the material. So several studies suggested that the crack initiates when there is a high local misorientation, and the density of geometrically necessary dislocations is closely related to the local misorientation. So basically there are two types of dislocations in the material: statistically stored dislocations and geometrically necessary dislocations. So whenever geometrically necessary dislocations are a non-zero Berger vector. So whenever geometrically necessary dislocation comes, there will be a local change in misorientation, and using EBSD we can detect this change in misorientation. And from the literature, it's very clear that various misorientation parameters has already been correlated with the degree of damage due to plastic strain, fatigue, creep and cavitation. So coming to the first part of my study, at location 1, 2 and 3, here is the weld. So location 1 is the area near the weld and somewhere middle of the crack and at the crack tip, and the crack length is around 18 millimeter in length. So the orientation map shows a random texture around the crack, but when we are coming to the grain boundary maps, it's very clear that the low angle grain boundaries, you can clearly see high concentration of low angle grain boundaries which are marked in red along the crack, along the grains near to the crack, and especially at the weldment. And from the literature, it's clear that low angle grain boundaries corresponds to areas of dislocation density. So I'm using two EBSD misorientation maps to look at the plastic deformation. One is a kernel-based approach to understand the local strain variations, and another one is a grain-based approach to identify the local change in plastic strain in a grain scale method. So in kernel-based methods, in order to find a kernel average misorientation at the point I, it basically takes the average of all the elements, pixels around the kernel, and it excludes all the elements outside the grain boundaries. Similarly, for grain reference orientation deviation, first it takes the average misorientation within a grain, and it takes the difference between the average misorientation with each pixel, and the average of the entire grain gives the grain average misorientation. So coming to the kernel average misorientation maps, it's very clear that the misorientations are more accumulated around the grain boundaries, especially on the region closer to the weld. And I have taken misorientation less than 2 degrees for kernel average misorientation, and this also has shown to be a good measure of geometrically necessary dislocation density. So from the KAM maps, dislocations with low KAM values were more prominent at the crack tip, and dislocations kernel average misorientation up to 1.2 degrees were predominant in the weld region, which shows a heterogeneous deformation near the weld. So both kernel average misorientation maps and grain boundary maps shows more intense deformation at the grain boundaries, and especially towards the weld region. So this can be attributed to the inelastic strain accumulation around the voids. So considering the grain scale methods, it also showed a similar trend to the KAM maps, but this shows more intragranular misorientation within the grains. So the lower GROD values towards the crack tip can be associated again with the reduction in density of cavities. And also from the both the misorientation maps, it seems that misorientation maps are helpful in predicting the direction of crack propagation. So I have done micro hardness measurements along the crack. Hardness values has been shown to be proportional to the square root of dislocation densities. And misorientation maps and hardness maps qualitatively gave the same results, but it's difficult to compare both the methods because of the difference in spatial resolution and the extent of strain fields they sampled. Now coming to the second part of my talk, where I am comparing small angle neutron diffraction results with respect to EBSD. So this was based on a work presented by my supervisor Hedia. So she has done sands at different points along the line B2. So I also did EBSD measurements at those locations, and it seems that I am getting similar trends with respect to sands and EBSD. And you can see in the sands results the cavities reduces in that direction, and which I am getting similar trend in EBSD as well. The more the curve shifts towards the right, it means that there are more cavities, and you can see that the cavity location 2,5, which is the far end, it comes closer to the lower end. So from this evidence, it suggests that the EBSD misorientation maps, KAM and GROD, might be correlated with the cavity densities. So that concludes my results. So I have studied the plastic strain around a reheat crack using EBSD, and I have compared the results with a micro hardness survey. And KAM and GROD maps revealed higher levels of lattice misorientations in the weld region where the crack is initiated, with strains mainly concentrated at the grain boundaries. And these maps seems to be effective in identifying cavity nucleation sites with SEM images. So I would like to acknowledge EDF Energy for funding the project and Open University for giving me a platform to conduct my research. Thank you.